We're going to talk briefly about the history of atomic theory as we start to describe the parts of an atom. So around 1800, a man named John Dalton came up with this theory that helped us understand an awful lot about matter. He had these 5 postulates. First, matter is composed of small particles called atoms, and the atom is the smallest unit of element that can participate in chemical change. We talked about that in the review module. Number 2, an element consists of only one type of atom, and it has a mass that's characteristic of the element, etc., etc. So basically, all atoms of the same element have the same properties. Number 3, atoms of one element will be different from atoms of all other elements. So an atom of copper will be different than an atom of helium. Number 4, a compound consists of atoms of 2 or more elements that are combined in a small whole number ratio. And in a compound, the number of atoms of each of the elements are always present in the same ratio. This is going to lead us to the law of constant proportions. Number 5, atoms are neither created or destroyed during a chemical change, but instead they are rearranged and they yield substances that are different from what was present before the change. That's the law of conservation of mass. Now, the law of conservation of mass states that matter cannot be created or destroyed. It will only change its form. So if we have these 2 green atoms and we have 2 blue atoms and they combine together, we should have 2 of our products, 1 blue and 1 green, added together. Now, the law of definite proportions and the law of multiple proportions. There are an awful lot of words here and they can get confusing, but it's easier to show you with some numbers. But the law of definite proportions will state that a compound will always contain the same ratio of either atoms or masses of the same elements. And this is why H2O, which is water, is going to be water regardless of where you are in the universe. 2 H's combined with 1 oxygen is water. That's the law of definite proportions. And we can use experimental masses in order to prove that. So if we have, for example, experimental masses where we have these samples and they've decomposed into some amount of carbon and some amount of hydrogen, we can use that data to create a ratio. As long as we have all the carbons on the top and the hydrogens on the bottom, what we'll end up with is the same ratio, 5.33, and this is where I am. We end up with the same ratio, 5.33 grams of carbon per 1 gram of hydrogen. That is the law of definite proportions. Now, with the law of multiple proportions, when we have data like that, and it doesn't look like it's quite right, but we can compare our ratios and end up with whole numbers with an example. So if we have this data, so we have compound A, and compound A has 4.27 grams of carbon and 5.69 grams of oxygen. But B has 5.19 grams of carbon and 13.84 grams of oxygen. So now, I'm going to use the larger number to put on top, 5.69 grams of oxygen, and I will compare that to 4.27 grams of carbon. And then for B, 13.84 over 5.19. And when I put that into the calculator, then I get a ratio. So A is 1.33 grams of oxygen per every gram of carbon, and B is 2.67 grams of oxygen for every gram of carbon. So the question is this an example of multiple proportions or neither? And what do these data tell you about the substances? Well, this is the law of multiple proportions. It's not definite proportions. If it was, this would be the same. But this is the law of multiple proportions, because if I take that 2.67 and I compare it to 1.33, so I'm taking B and comparing it to A, what I get is a whole number. It tells me that I have the law of multiple proportions working here. And looking at these ratios, what I can tell is A and B are different compounds, and I can tell that B has twice as much oxygen per carbon. Now, after the 19th century, so around 1900, there was a man named J.J. Thomson. J.J. Thomson got his hand on a cathode ray tube. And I'm not going to give you too many details, but what he found with that cathode ray tube is he found that there were these little particles that were negatively charged. And since he found that these particles had a mass more than 1,000 times less than that of an atom. So he found this really small particle. And we ended up calling it later an electron. Now, Millikan, in about 1909, he created this oil drop experiment. And so what he did was he dropped wee little droplets of oil that he charged with an X-ray. And when he charged that with an X-ray, he was able to calculate the charge on those oil droplets. By calculating that charge, he ended up finding not only the charge of an electron, but also the mass of an electron. Thomson's research had led us to a charge to mass ratio. So what happened is all of these guys are working in order to figure out how are atoms structured. Now, we have two theories at this point about what an atom looks like. We have what's called the plum pudding model. So we have this kind of ooze, this goo of positive and electron parts. We know we have electrons. Or we have a model that looks a little more like Saturn. So you have this positively charged center matter stuff, and then you have this halo of electrons. Then Rutherford came along, and Rutherford came along with this gold foil experiment. Now, the gold foil experiment is found in every general chemistry book you will ever see. So what Rutherford did is he took some alpha particles and he beamed those alpha particles at a really thin, small piece of gold foil. And then he watched what happened. So some particles were significantly deflected. A few of them were a little bit deflected, but most of them passed straight through. And because of this experiment, he was able to determine that the volume occupied by an atom consists largely of empty space. He was also able to determine that there is a small, relatively heavy, positively charged body, which we call the nucleus, at the center of each atom. So now we know we have a nucleus, and in that nucleus we know we have protons. We also know we have electrons that are basically in this halo-like ring structure on the outside of the atom. But then we ended up finding out that some atoms that are chemically identical will have different atomic masses. So what this led us to learn was that we have neutrons as well, and those neutrons can vary in what are called isotopes. So it's atoms of the same element, but they differ in mass because they have a different number of neutrons. So now we've found the electron, we know we know its mass, and we know its charge. We know we have a collection, a nucleus that contains protons and neutrons. Now we're going to work with what to do with those particles.